The topic that we are going to see today is numerical based on memory hierarchy or organization. First we will see the formulas, and once we see the formulas then we will see the numericals. Okay, so in memory hierarchy the first formula is for a single level. In single level the time for a memory access is equals to time to access the cache plus 1 minus hit ratio into time to access main memory. Now see what exactly happened in the memory hierarchy. First there is a CPU. Okay, so first level is a CPU level. Then second is a cache 1, that is latch 1, and cache 2. Now we will take some time to access this from latch 1, that is nothing but a time 1, and we require some time for access from latch 2, that is time 2. So for single level CPU is there, L1 is there. That's why the cache time plus 1 minus hit ratio into main memory access time. For two levels where we can see L1 and L2. Therefore, T1 time to access and the hit ratio of level 1. 1 minus H1, that is the miss ratio. This is 1 minus H1 is nothing but a miss ratio. Okay, this is miss ratio. H1 is the hit ratio. So this is the time for T1 plus T2 because it is a two level hierarchy. Now here TA is equals to T1 into H1 plus 1 minus H1 into T2 plus twice T1. Why this twice T1 is considered? Because here we are considering the placement time also. Here we have ignored the placement time. Okay, so that's why here 2T1 is considered. Similarly for multi-level, there can be L1, L2 and so on. So that's why T1 plus 1 minus H1 into T plus 1 minus H1 and 1 minus H2 into T plus and so on. Okay, so this is how the memory hierarchy will be work. For a single level, you don't have to take here hit ratio, just time to access the cache plus miss ratio and time to access the main memory. This is time to access the cache and this is miss ratio and this is the time to access the main memory. Okay, so now let us see some example that has been asked in GATE examination. The first question that we are seeing, or the first example that we are seeing, is the example that is asked in GATE 2017 paper 2. Okay, now let us see what is the question. The given information is there is a instruction cache, there is a data cache and there is a L2 latch. The read access time for this is 2 nanosecond, 2 nanosecond and 8 nanosecond, and the hit ratio is 0.8, 0.9, 0.9. The main memory read access time is 90 nanosecond, and they are asking us what will be the average read access time. It is given that for a complete program there are 60% instruction fetch operations and 40% are operand fetch operations. Okay, so your operations has been divided into two types, instruction fetch and data fetch. For instruction fetch we are having 60% of instruction fetch operations, and for operand we are having 40% of fetch operation. Now what we have to calculate is the average read access time. Now let us first apply the formula for average read access time. Now see, read access time has been divided into two. 60% is the instruction fetch, so 0.6 into, and 0.4 is the data or operand fetch. So 0.6 into average read access time for instruction into average read access time for operand. Okay, this is 60%, that's why 0.6, this is 40%, that's why 0.4. Now we have to calculate this one, that is average read access time for instruction. So average read access time for instruction. Okay, now see what happened in instruction. If the instruction is there, we just need 2 nanosecond if it is in a cache. Okay, plus if it is not in a cache, then miss ratio means 1 minus 0.8, that is nothing but 0.2, into if it is not in a cache, then we have to go to L2 cache, so it will require 8 nanosecond, plus if it is not in a L2 we have to take it from a main memory, so therefore 1 minus 0.8 into 1 minus 0.9 into main memory access time, that is 90. Okay, so the values will become 2 plus 0.2 into 8 plus 0.2 into 0.1 into 90. See, this is the latch hit. Catch a hit. Catch a miss, that is 1.08, and the L2 catch a memory access time. L2 miss as well as I miss. Okay, if you want, you can write down the miss ratio here also. Okay, write down the miss ratio for this 0.2, 0.1 and 0.1. Okay, so this is the average read access time for an instruction. If you calculate this, it will going to come nearly about 5.4. Okay, all the units are in nanoseconds, so definitely this time will also in nanosecond. Then next we have to find out the average read access time for operand. For operand, it should be, first we are going here, there for 2 nanosecond, plus we miss this, therefore 0.1 miss, and we will go to the L2 cache, that is 8 again, plus first miss, then latch also miss, then we will go into the main memory, therefore 99. See, this is 2 for the data cache, plus if this miss ratio into, we will go to the L2 cache, plus this is also miss, this is also miss, then we will go into the main memory. This value will going to come nearly about 3.7 nanosecond. Okay, so these values we will keep in the first formula. Therefore, it becomes 0.6 into 5.4 plus 0.4 into 3.7. So the total value is coming around 4.72 nanosecond. So your final answer is 4.2 nanosecond. Again, see what we have done. We have to calculate the average read access time. The read operation is divided into two parts, that is instruction fetch and the operand fetch. 60% are the instruction fetch and 40% are the operand fetch. Okay, so that's why 0.6 and 0.4 into average read access time for instruction, average read access time for operand. Then average read access time for instruction is equals to, first if the instruction is a cache, then only 2 nanosecond will be required, that is the hit, plus if it is not in a I cache, then we have to go for a L2 cache. That's why the miss of I cache and hit of L2 cache. Plus if it is not in a I cache as well as not in a L2 cache, then we have to go for a main memory. That's why 0.2 into 0.1 into 90. Okay, similarly for operand, and then we put all the values together, and this is what the final answer will come. Okay, let us see the another example that is asked in a GATE 2015 paper 2. They are directly given the cache hit time is 5 nanoseconds and the ratio is 80%. This is hit ratio and this is the time, and they are directly asking you what will be the effective access time for this cache. So here we have to know, don't have to do anything, just effective access time is equals to hit ratio into time plus miss ratio into time. If it is a cache hit, then 0.8 into 5 nanosecond will be required. If it is a cache miss, then 0.2 into 50 nanosecond will be required. So that's why it becomes 14 nanosecond. It's a very simple. Hit ratio is given as well as hit time is given. Similarly, miss ratio is given and miss time is also given. So we have to just apply the formula hit ratio into time plus miss ratio into time, and the answer is 14. Such type of question is asked in 1 marks question only. The previous question which we have seen, generally such type of questions are asked for 2 marks questions. Now let us see the other example. It is asked in GATE 2014 paper 3. Okay. Now let us see what is the question in GATE 2014. We have given a translation look-aside buffer. The time to access this TLB is 10 millisecond. If we are accessing physical memory, the time is 80 millisecond. Okay. And the TLB hit ratio is 0.6. Therefore, this implies that TLB miss is 0.4. Okay. This data is given, then we can conclude that TLB miss is 0.4. And they have asked you to find out effective memory access time. Now see, if main memory, instead of main memory, physical memory time access is given. So all this TLB and all the data is in a physical memory. So extra time will be required to fetch the data from a physical memory. Now let us see what will be the formula for effective access time. For effective access time, first TLB hit, then if TLB hit, then the time required is TLB memory access time as well as physical memory. Why we are counting physical memory? Because all the data is in a physical memory only. Plus, if it is miss, TLB miss, then we require TLB plus 2 physical memory access. Now see, if you remember our diagram, we are trying to access this TLB. Okay, this TLB is already in a physical memory. So the time required to access the TLB as well as the physical memory. Okay, we will see the TLB, and from TLB we will see for the physical memory. Translation leukocyte buffer is just having the mapping like. Then if it is not there, it is not in a TLB, then we have to look for the PM 2 times. This is our TLB. Okay, this is our CPU. So CPU first fetch the data from TLB, and then TLB will fetch the data from physical memory. But if it is a miss, that the data is not in a TLB, then we have to go for the physical memory for this TLB also and for data also. Okay, so therefore this happened. Then here the hit ratio is 0.6 into TLB memory access time 10 plus physical memory access time 80 plus TLB miss is 0.4. TLB memory access time is 10 plus twice of that is 160. Therefore total is 54 plus 68 is equals to 122 millisecond. All the units are in millisecond, therefore the final answer that we are getting is also in a millisecond. Now see what we have done. Here instead of cache memory we are having translation leukocyte buffer. First we will see the data whether it is present in TLB. If it is present in TLB, then we will access that data from main memory. Okay. If it is not present in TLB, then we have to access the main memory twice, main memory or a physical memory. That's why our formula has become hit ratio of TLB, therefore TLB plus physical memory. Miss ratio of TLB, TLB plus 2 of physical memory. So this is what the final answer we are getting. So such type of questions has been asked in memory organization. You have to remember the formula and from where we are fetching that data, whether we are fetching that data from cache, from main memory or the physical memory. So whatever is there, we have to take care of this hierarchy. Directly we are fetching from main memory, directly we are fetching from physical memory or directly from the cache. Okay, thank you.